My name is Dongsu, and I'm going to be presenting our work entitled Foresighted Decisions for Vehicle Innovation, an offline reinforcement learning approach. I first introduce motivation and background in terms of the reinforcement learning with the autonomous driving system. And I will share about the proposed solution and its performance and compared to the vanilla reinforcement learning. And I will end my speech with the conclusion. Okay. Autonomous driving system is attracting attention in academia and in industry, and we can divide this system into two folds: the recognition and decision-making abilities. And with the success of the neural networks, the recognition ability have been extremely developed. However, in the case of the decision-making abilities, much improvement points are still needed. So, in the previous work, how do we endow the decision-making ability into autonomous driving system? The one promising solution is online reinforcement learning. The online reinforcement learning refers to a modern incarnation of learning-based control. And this learning methodology has following properties. The agent wants the polish through the trial and error with a real-time interaction and actively collect the trajectory data. And reinforcement learning follows the Markov property that the agent's bases its action considering only current information. So in this moment, I have one question. So do you really want to apply it into mission-critical system? So I reckon that it's hard to apply into the mission-critical system. So online reinforcement learning has a few challenges. This methodology is hard to apply in the mission-critical system and high cost for the data collection, and it's based on the short-sighted decision-making. So in this work, we aim to adopt the offline paradigm and develop foresighted decision-making on model-free reinforcement learning. So what is the offline paradigm? Actually, we are already familiar with the offline paradigm due to the imitation learning. The offline paradigm is a learning methodology that finds the polish based on the previously collected data set. And so, what are the major differences between the imitation and offline reinforcement learning? So I can say the two folds: the data format and the learning mechanism. The imitation learning only considers the state and action pair as a data format, and it is based on the supervised learning. And conversely, offline reinforcement learning follows the data format and the learning mechanism with the reinforcement learning. So, what situation can be each method be applied in? So, the imitation learning cannot evaluate the state and action pair, and it just mimics the trajectory behavior. But on the other hand, the offline reinforcement learning can estimate the value of the state and action pair based on the real signal. So, and this difference makes the big difference. And when we have the expert demonstration data set, the imitation learning is a good solution. So, however, on the other hand, when we don't have the expert demonstration, it means that we have a suboptimal data set. The imitation learning cannot function, it cannot work on this data set. So good alternative is offline reinforcement learning. So before diving into the proposed solution, so there is a simple example to comprehend our concept of our proposed solution. So let's imagine this driving scenario. In this scenario, the red vehicle is the agent of the reinforcement learning. In this scenario, this agent's rational option is maybe switch the right lane to secure the driving space. But however, the blue vehicle on the most right lane can make a decision to switch the left lane, and in this situation, the red and blue vehicle makes a car crash and collision, and we can say it's a bad case. So on the other hand, in the foresight decision making, the agent first foresight the future information we call the EFT state, and it means that the red vehicle can predict that the blue vehicle on the most right lane can make decisions, turn left, and in this scenario, the red vehicle's most rational option is to keep straight and drive straight, and we can say it is a better one than the former case. Okay, so let's take a look at this traditional model, the traditional model between the vanilla reinforcement learning and our proposed solution. In the reinforcement learning, vanilla traditional model is really simple. This single state transition composes that the entire agent observes the state and bases their action after that encountering the next state. The sequential overview can be is similar to this extensive form game, such as like chess or Go. And in this outlook, we can divide the single state transition into two steps. And first step is a foresight step, so which simulates the EFT state, the future information, reflecting other agents' actions except for the self-agent action. And next step is the decision-making step, and in this step, the agent can make a decision based on the future information. And this view and this outlook can enable the agent to make an adaptive decision-making by leveraging the future information. So the most important question is how do we implement it in practice? The proposed solution has two different steps, the prediction step and reinforcement learning step. In the prediction network step, we include the prediction network that can foresight the EFT observation based on the current observation. And this network is based on the supervised warning with the MSE loss function. And this loss function aims to minimize the error between predicted and true EFT observation. And next is the reinforcement learning step. And in this step, we can employ any type of the reinforcement learning algorithm. And in this case, we only focus on the actual critic network, actual critic algorithm, and the actual and critic networks are to approximate the published and the state and action value function. And the objective function is followed with the same, so with the binary reinforcement running, but we consider the EFT observation so as a highlighted red line, and instead of the current observation. So if you want to check the mathematical completeness of the proposed solution, our paper includes, so please refer to it. So let's take a look at the simulation setup and result. And in this simulation, we consider the two different scenarios, the highway and lane reduction scenario. But in this presentation, we only focus on the highway scenario, and we contemplate the three different data sets: the final, medium, and random data set. And these data sets are generated by the online reinforcement learning agent with a DDPG algorithm. So, and final is trained by the fully trained, and medium is the early start, and random is the uniform random policies. And these two figures is shows the online reinforcement learning performance, and left one is the driving time, and right one is related to the episodic cumulative reward. And this result confirms that the online reinforcement learning agent is well trained by converging the performance. And so, based on this setup, we compare the offline reinforcement learning and our proposed solutions performance on the highway traffic scenario. And we benchmark the three different algorithms, IEL, BCQ, IQL, and these three different algorithms are most representative in the offline reinforcement learning community. And the numerical result confirms that our proposed solution achieves better performance in 8 out of 9 tests, so it is really powerful as we saw in the highway traffic scenario. Okay, it's time for the conclusion. So in this work, we employ the offline reinforcement learning to enhance its practicality, and we propose the episodic visual thinking-based reinforcement learning and EFT reinforcement learning. And the simulation results confirm that the proposed solution outperforms and surpasses the performance better than this binary reinforcement learning, and specifically achieves better performance in 8 out of 9 tests on highway scenario. Okay, thank you for listening, and do you have any questions?